An interesting fact about the formula for matrix multiplication is that it works just as well if the matrices are described as blocks of other matrices rather than just blocks of numbers. So in this formula where we have the sum of aij times, or aik times bkj, everything goes through just fine if aik and bkj happen to be matrices rather than scalars, so long as the sizes of the individual pieces line up correctly. So that sounds a lot more confusing than it really is. It turns out to be quite simple in practice. So here are a couple of example matrices. Here I've got a matrix which overall is 2 by 3. However, we can write it in terms of two blocks. One block D, which is 2 by 2, and a block E, which is 2 by 1. Or here's another example of a 3 by 3 matrix written in terms of 4 blocks. F is 2 by 2, G is 2 by 1, H is 1 by 2, and J is a scalar 1 by 1. Now you're not completely free to determine the sizes of these things. When I draw the blocks, I have to use vertical lines, straight lines, either vertical or horizontal, in order to break the matrix into different pieces. And that puts some restrictions on the sizes of the different blocks. The number of rows in F had to be the same as the number of rows in G, and so on. But those rules are very natural. And then if we look at the product of these two block-defined matrices, well, DE, I could think of that, if I just look at the letters, I could really think of that now as a 1 by 2 block matrix. And FGHJ is really a 2 by 2 block matrix. And so if I think of this as 1 by 2 times 2 by 2, then the result is also going to be 1 by 2, right? So I have one entry here and an entry here. And if you think in terms of an inner product of a row with a column, I should get DF plus EH. That's exactly what I have here. Now D, remember, is 2 by 2, and F is also 2 by 2, so DF is 2 by 2. E is 2 by 1, and H is 1 by 2, so EH and DF are both 2 by 2, so the whole thing here is a 2 by 2 block. The only way you can add matrices together is if they're exactly the same size. Similarly, on the other block, I have DE times GJ, so that's DJ, or DG plus EJ. DG is going to be 2 by 1, and EJ is also 2 by 1. So therefore we can add them together, and we get overall a matrix which has got 2 rows and 3 columns, as it must. But it will be equal to the product of the original full-sized matrices. So that's a neat trick, but what's the importance of it? Well, the most important case is when we start writing a matrix in terms of its columns. So here we have a matrix X, which is m by n. And if I think of it in terms of its columns, I'll write the vectors x1 through xn. In fact, we're going to do this so often that we'll make this notational connection quite a bit. Well then, if I take a times x, well, in the block sense, a is 1 by 1 and x is 1 by n. And so we can just take that 1 by 1 and move it inside and multiply each of the column vectors. In other words, a times x is nothing more than the collection of a times each column of x. And then if we look at a product like that, which is a matrix times a vector, so here x is our matrix again. Now we have a vector v of length n. So we have the columns of x, right? This is still m by n. Each of those x's, xj's, is actually an m by 1 vector. Okay, v is itself a vector, so each of these v's is a scalar. It's a little unfortunate, but quite common that we don't make any distinction notationally between scalars and vectors like we do in vector calculus. You're just going to have to know that in this case the x's are vectors and the v's are scalars from the context of how they were created. But now, if you just look at the letters and think of it in block structure, it looks like a block inner product. And in fact, we have v1x1 times v2x2 and so on. Now, I played a little subtle trick here. We should always be careful about the order of our products. So I should have had x1 v1 here, and x2 v2, and so on. But now v1 is a scalar, so it really is independent of the order, and we can just say v1 times x1 if we like. Okay, so what I'm doing is I'm taking each column of x, multiplying by a scalar to get a vector, and then I add all those vectors together. In linear algebra, that's what we call a linear combination of the columns of x. So a matrix vector product is a linear combination of columns. Here you can see that demonstrated with numerical values. So here, if I think of this matrix in terms of its 3 columns, then the matrix times the vector, I take 2 times the first column, 0 times the second column, and -1 times the third column. Those are individually easy operations to do, and then I add those 3 vectors to get the result, 4, -2. Now that means that if I had a matrix-matrix product, okay, notice that this column here is the same as the first column down here. So remember, this is like our example earlier of a times x. All right, I'm going to use this rule here. A times x is the same as taking a times each column of x. So that would mean that here's my a, right? Here's the first column. Well, I just did that computation up here. That answer is the same as the answer that we got before. Then in the second column, right, this is some different linear combination of the columns of A, and this is some third linear combination of the columns of A, and we would get different answers. Okay. Now there's something similar. Instead of having a matrix on the left and a vector on the right, we can have a vector on the left and a matrix on the right. Now, in this course, we are going to prefer column vectors. If we write down a vector, we mean a column vector unless we specifically say otherwise. And the trick for pulling that off in general, because we do need rows sometimes, is to use transpose. So remember that a transpose, right, reverses or swaps rows and columns. So in other words, what were rows before become columns, what were columns before become rows when you take a transpose. So if you take the transpose of a column vector, 1, 2, 3, then it's just the row vector, 1, 2, 3. Okay, so this way, whenever we write y1 transpose, we know it has to be a row vector. So here I have a matrix Y, and I'm breaking it down in terms of its rows. Then if we multiply by a vector on the left, okay, again I want column vectors, so in order to make it a row vector I have to use W transpose. So W transpose is going to be 1 by M. And let's say Y is M. We know it has M rows and N columns. Well, then again, in block form, this looks like an inner product, and we have W1 Y1 transpose plus W2 Y2 transpose, and so on all the way through, adding them together. Okay, now I'm taking a scalar times a row plus a scalar times another row, and so on. It's a linear combination of rows. So the very important connection to remember here is that when you multiply on the right side of a matrix, you operate on the columns of that matrix. And when you multiply on the left side of a matrix, you operate on the rows of that matrix. And here, operate means take a linear combination. Now this is all still the same kind of matrix products that we started with from the definition. But having these alternative ways of doing things turns out to be a very fast way of thinking in a lot of important problems. So here's an example where we have A, which is a 4x3 matrix. I'm just going to put in dots to represent the values because we don't care what they are. And I want to represent the operation of multiplying the first column of A by 1, multiply the second column of A by 2, and multiply the third column of A by 3. Right? Well, to solve that, right, we're taking a particular kind of linear combination. So first we multiply the first column by 1, and then we add 0 times the second column and 0 times the third column. If we want to multiply the second column by 2, well, we take 0 times the first column, 2 times the second column, 0 times the third column. And then finally, we do it again. We take 0 times the first column, 0 times the second column, and 3 times the third column. So whatever A is, if I multiply A by this matrix on the right, I'm operating on the columns of A in such a way as that in the first column, I just take 1 times A1. In the second column, I just take 2 times A2. And in the third column, I just take 3 times A3. As another example, suppose we have a 3x3 matrix, and I want to just add the rows together. Well, that's a linear combination of the rows, where the coefficient of each row is 1. So all I have to do is multiply on the left by the row vector 1, 1, 1. And that will add the 3 rows together. It's always a useful check at the end of a problem like this to see whether the sizes actually work. So in the first example, I have a 4x3 times a 3x3, so the answer is defined and 4x3, and that's correct. We wanted an answer the same size as A. Here I have a 1x3 times a 3x3, and the answer is 1/3. That's what you should get if you add up the rows of a 3x3 matrix. Finally, let me say what all this has to do with MATLAB. So we've already seen that to extract a block from within a matrix, you use the parentheses notation and the colons to define which rows and which columns to select. Similarly, if you want to build a matrix out of blocks, well, you use the same notation that you use for scalars. You use the square brackets with commas to separate columns, semicolons to separate rows. As long as all the sizes line up internally, you'll be fine and you get the answer that you want.